I'll read it. I have a hard time. I'm gonna try really hard to read it once, then write down the information, then read it again. So problem number 30 says a 1,200 kilogram automobile travels at 90 kilometers an hour. Here are the questions. What is the kinetic energy? And what is the net work required to bring it to a stop? So now let's reread it again. So this is problem number 30. And it says that a 1,200 kilogram vehicle, so we have a vehicle here, and since, shut up, down, police car, so it's 1,200 kilograms. All right, and it says that this 1,200 kilogram vehicle is traveling at 90 miles, or not 90 miles, it's 90 meters or kilometers per hour. Okay, cool. So this is a mass. Then it says this thing is traveling with a velocity of 90 kilometers per hour. Uh-oh. Then it asks us, what is the net work and kinetic energy? So part A says, what is the kinetic energy? Part B says, what is the net work? Okay, it would take to stop this thing.
Kilometers per minute.
Well, hold on a second. Yeah, it's per hour. So I know this formula here. Right? And we have a mass and we have a velocity, but why is it that I'm just not plugging in that 90 yet?
Because
So wait, isn't there initial velocity and final velocity?
Yeah, well, in this case, it's just the velocity because the velocity doesn't change according to the way that they describe the problem. Okay? So I guess the question I'm asking you guys is why is it that I'm just not saying 1/2 times 1,200 times 90 squared? I can't do that. I heard somebody say what?
Cole said it like 90 times per second.
It's got to be meters per second. So I'm gonna convert this from kilometers per 1 hour, and then how many seconds are in an hour? Can somebody rattle it off the top of their head?
3,600.
Very good. 3,600 seconds in 1 hour.
You said it.
Shout out to Bracy. Now how many kilometers? Or wait. How many meters are in a kilometer? 1,000. Good. Now, remember, I can flip-flop these anyway, but why did Mr. Adams write the meters on top and kilometers on bottom?
Want over given.
Because it'll cancel out the other.
I want this to cancel with this. And I want this to cancel with this. So really what I have is I have 90 times 1,000 on top, which is just 90,000, right? All over 3,600. And when I'm done, I'm left with meters per second. So get out my handy dandy calculator, and I'm going to say 90,000 divided by 3,600, and that's 25 meters per second. Is that right?
Yeah.
Is that what you guys got? Probably should check my notes. It'd probably be helpful. But anyways, what I found is that the velocity is 25 meters per second. And that's what I have to have before I can plug it into the formula. So let me double check my notes. Peruse my notes. That is correct. So now to find the kinetic energy, I'm just going to say 1/2 times 1,200 times 25 squared. And that gives me my kinetic energy. So let's do that. 0.5 times 1,200 times 25 squared. Wow. That's a lot of energy. Double checking my notes. Yep. They round to significant figures, so they rounded it to 3.8 times 10 to the 5th. Okay. So let's do what the textbook says so there's no confusion. That number is actually, it's rounded, so I should probably do a squiggly line and say 3.8 times 10 to the 5th joules. And I could say joules with confidence because I did not forget to convert. So if you go to do this problem and you get the wrong answer in the back of the book, what's the first thing you should check? Your conversions. Make sure that it's in meters per second. Make sure that it's in kilograms because they don't always give it to you that way. All right, so now work. The second part of the question says, how much work will it take to stop the vehicle? Well, work is actually equal to delta K. And delta K, your difference in kinetic energy, remember, is the final kinetic energy minus the initial kinetic energy. Well, what is the final kinetic energy? So I guess earlier somebody said, Mr. Adams, is that the initial? I guess so, if we think about the second part of the problem. So now how do we find the final kinetic energy? So to find the final kinetic energy, it's real simple. We're just going to say that the final kinetic energy is equal to 1/2 times the mass, which is 1,200. But if this thing's coming to a complete stop, what will be the final velocity? 0. So what's the final kinetic energy? 0. So my final kinetic energy will be 0. Keep that in mind. It'll be helpful on our roller coaster lab. So delta K then is equal to 0 minus, what was the initial kinetic energy? This stuff here, right? So it's 3.8 times 10 to the 5th joules. So my work, my net work, which is equal to delta K, is equal to negative 3.8 times 10 to the 5th joules. And that makes sense, right? If you have an object that has a kinetic energy of 3.8 times 10 to the 5th joules, it would take that much energy to stop it.